Yes.
Okay, so hello everyone. I hope you all had a good start into the new year of 2022. And welcome to the webinar series on rate splitting multiple access organized by IEEE ComSoc WTC Special Interest Group on RSMA. And today is actually our final webinar, and it's our great honor to have Professor Wolfgang Utschick from Technical University of Munich as our distinguished guest speaker. So please allow me to make a brief introduction of Professor Utschick. Professor Utschick is a fellow of IEEE. He received the diploma and the doctoral degree from the Technical University of Munich. And since 2002, he has been a professor with the TUM, where he is chairing a signal processing group. And since 2011, he has been a regular visiting professor at Singapore's new autonomous university, the Singapore Institute of Technology. And since 2017, he serves as the Dean of the Department of Electrical and Computer Engineering. He held several patents in the field of multi-antenna signal processing and has authored and co-authored a large number of technical articles in international journals and conference proceedings. He edited several books and is founder and editor of the Springer book series, Foundations in Signal Processing, Communications, and Networking. He has been a principal investigator in multiple research projects funded by the German Research Fund and coordinated a German DFG priority program on communications over interference-limited networks. Professor Utschick is a member of the VDE and leading a member of the expert group 5.1 for information and the system theory of the German Information Technology Society. He is currently chairing of the IEEE German Signal Processing Section. He was recently appointed as a core member of the newly established Munich Data Science Institute at TUM and is the PI of the just launched 6G Future Lab Bavaria and the 6G Live Research Hub of the German Federal Ministry of Education and Research. So before Professor Utschick's talk, I would like to remind the rules of our webinar. During the 15-minute talk, please keep yourself muted and you can type your question in the chat box. And after the talk, we will have a 10-minute Q&A session. You can unmute yourself to raise question, or I will choose 2 to 5 questions from the chat box. Okay, enjoy the talk. So let me stop sharing. And Professor Utschick, you can share your screen now.
So let me share this here. Can you see
Yes.
my slide fully? Yeah.
Yeah. Maybe you can use the full screen
Yeah,
view.
I have to do so. Yeah. Oh, sorry. Yeah. Oh. I have to stop it once more again. Sorry.
No worries.
To do this now. How to rotate it?
Maybe at the right top.
Yes, this is it. So, come on. I have a problem. I have never this problem. Now I have it. Okay. Come on. Just give me a second.
No worries.
I have to upload it again. It's the best way to do it. Okay, now. Hey, what's this one? Ich verstehe es nicht. Sorry. I have to change the viewer. It seems to be an interference of the Zoom with the Acrobat reader. This is a new phenomenon for me. Sorry. So now. Here we are.
Yeah, perfect.
Okay, so sorry for this stupid issue. Once more again, or let me introduce myself, Wolfgang Utschick, TUM. Thank you very much for the nice invitation and introduction to this talk. Thanks to the organizers, Lina and Bruno. That's a great opportunity to report about our work. I slightly changed the title, not the topic, of course, but I slightly changed the title because I found it a bit too long. It's called Rate Splitting, of course, in this webinar, in FDD massive MIMO systems based on second-order statistics of transmission channels. And this is a joint work with Donia, who is a PhD student in my group, and with my colleague, Michael Johann. So let me first start with the motivation and the system setup here. So we all know about massive MIMO systems. We all know about frequency division duplex systems. And the first thing is that in FDD systems, the typical or useful uplink downlink reciprocity of channel state information is broken. So due to this, we have to find some workarounds, some feedback of channel state information or something like this. And due to the massiveness of antennas, the coherence interval is much too small, yeah, too little coherence in order to estimate the channel efficiently. So we need too much resources for estimating the channel, and that leads to, so we observe limited training intervals, and that leads to pilot contamination and to incomplete channel knowledge. So in this talk, how do we try to compensate for this? So we combine a couple of methods. So the first one is that we try to exploit, instead of instantaneous channel state information, we try to use second order statistics to design what we in some previous work called a bilinear precoder. There had been some controversial discussion if this is a good term for what we are actually doing. So you might only, but this is the other discussion, not for today. You might also consider it as a generalized maximum ratio combiner or a transmission matched filter. And we combine this with rate splitting, otherwise I wouldn't be here in this webinar today. We combine it with rate splitting because rate splitting is well known to be a very elegant method to cope with non-perfect channel state information. It can also be used for perfect channel state information. And we have seen some talks here in this webinar where it was used also for perfect channel state information, but it's well known for being a very proper method for having not perfect channel state information. And therefore we combine this because we will deal with data with channel state information which is corrupted by pilot contamination, which is not perfect. Yeah? And that's this combined with rate splitting. And in order to solve the appearing optimization problems, the third step, or the third method which we are combining with the other two, is that we apply some novel fractional programming techniques, which have been recently, 2018, I would say still recently, have been proposed by Kaiming Shen and Wei Yu in transactional signal processing. So once more again, what already said, we dedicate T downlink, TDL, resource blocks for the training. And our assumption is that this is small or even much smaller than the number of degrees of freedoms we have, means the number of antennas M. And that leads, since we have not enough observations in order to solve this inherent inverse problem, we will have a severe pilot contamination. So what we get at the end is here in equation 1, we get nevertheless an observation of each channel. The observation vector yk is an observation of the channel hk, and this observation is conveyed by using pilot data, which is contained in the matrix phi. And then we have some distortions and noise, however you want to model in the vector nk. And based on that, we want to design a statistical precoder. This is another name of what we call the bilinear precoder, and it works as follows. You get an observation yk. This is an instantaneous observation of the channel, of the instantaneous realization of the channel, but not perfect, heavily contaminated. And this observation is transformed to a precoder of the case user by a linear transformation of matrix AK. And this, the particular thing is here that YK, this is the observation of the channel, is an instantaneous information, and the PK is an instantaneous precoder for this moment. But AK is a deterministic matrix that just depends on second order statistics. So the question is how to find the optimum AKs, because we do not design the pilots. We do not manipulate somehow or change or decontaminate the observations. The only thing is what we want to do is we want to find optimum transformations AK that transform the observation to an instantaneous precoder. So that is our goal. So let me also say a few words about rate splitting. Also, this is really not needed in this webinar, I guess, because you're all experts in rate splitting, probably, or most of you. But nevertheless, let me say a few basics. Rate splitting is based on splitting up the user message in a common and in a private message. Yeah? And we pack all common parts of the users into one super common message, because the particular feature of a common message is that it is common, so it has to be decoded by all users. So therefore, we can only detect the data rate of the weakest user, because the weakest user, all users can decode the message of the weakest users, but the weakest user cannot decode would not be able to decode larger data rates. Yeah? This is a specialty of the rate splitting. And then we encode both messages separately. Yeah? We have a common message and we have private messages, and we call them the symbols SC. C stands always here in this talk for common, and SP1 up to SPK is the private messages for the private channels to the users. And then the transmit vector X is given by a linear combination of the precoding vector PC and the precoding vector PP, indexed by the number of the user, and the weighting is based on the symbols which are modulated on the signal X. And what is important is that the common precoder PC and the private precoders PP, K, that these precoders are functions, linear functions of the observation of the instantaneous observations of the channel. The precoder for the common data stream is a function of all observations of all users, because it's a precoder which is meant for all users. And the precoder for the private precoder of the case user depends only on the observation of the channel YK of the instantaneous information of the case user. It depends, of course, also on second order statistics of other users because of interference issues and so on. But the instantaneous part depends only on YK. And let me say a few words about the signal model. The received signal for the common stream is a bit different, like compared with the received signal with the private stream. Let's inspect this. The common data stream contains all portions of signal. You see here the inner product of the case channel, HK, with the precoder PC of the common data stream and with the precoders of the private data streams. This is what we would have expected in such a model. And whereas in the private data stream, you don't see the impact of the common data stream. This is because the following regime is considered in rate splitting, namely that the common data stream is decoded first at the receivers, and then we assume that we can cancel this portion of the signal that comes by the common stream completely from the signal. This is useful here. This assumption is valid here because we assume that we do not have full channel state information, or at least we have only contaminated channel state information at the base station, but at the receivers, we assume that we have full channel state information. So it's completely valid to assume that at the receivers, we have a one-step or one-stage successive interference canceller that after the demodulation of the common data stream, the common data stream signal portion is removed. And therefore, you see here on the top, in the bottom here of the slide, you see that the private data stream is not interfered anymore by the common data stream. This is a very important assumption in rate splitting, which we are doing here. So what you also see here, that the inner products here, these inner products of the channels with the precoder, so HK times PC or HK times PP, yeah, that these precoders, and here P is missing, I see it, that these inner products, they are here replaced by these values B, yeah, and the important thing is that at the transmitter, we have no access to the true values of this inner products B. That means that we have no correct expressions of the mutual informations, which are important for optimizing transmission strategies in order to achieving high rates. Yeah? We do not have these expressions correctly. So what we do instead is, and this brings me to the part of the objective function, we assume that we have estimates of these inner products. Yeah, and these estimates are estimates which come not by observations from the current instantaneous channel state information, they just come by the second order statistics. This is the assumption. And this is a decoupling of the instantaneous part of the stationary part of the second order statistics. So since not having the true inner products which play a role here for at the end finding the SNRs, we cannot work with the rate expressions, but we can work with lower bounds. And these are the so-called hardening bounds, which come from Medar and Hasibe and others. And they are lower bounds on the mutual information. And they are typically used in this setup and also in our previous work and work of others. So what we can do is we can say, okay, the unknown mutual information with respect to the common data stream and with respect to the private data streams, they are lower bounded by these typical expressions log of 1 plus an SNR expression. And here in equation 4 and 5, you find the SNR expressions for the common SINR and the private SINR. This is a signal to interference and noise ratio for the common data stream and for the private data stream. Once more again, what you can see here is that, as already before, the common data stream is interfered by itself because it's not a perfect channel state information, so it's interfering itself. And we have this private precoders. Whereas for the SNR expression for the private part, the common part does not appear anymore, as already mentioned before. So since here, these inner products, which we do not know, yeah, we just have estimates of this inner product, since we do not know this, we replace them by everything what we know about the second order statistics, and that is shown on the next slide. And what you see is here a very packed slide. Yeah? So let me just guide you through this slide. So we see equation 6 and equation 7, and these are the two SINRs that we were discussing before. And you see the typical pattern of such an SINR. It has this typical numerator, which depends on something which we want to, which is useful for the signal reception, and then we have interference in the denominator. And I would draw your attention just on the important parts here, and this is the vector AC. The vector AC is the vectorized matrix AC, and remember what was AC? AC is the transformation, the matrix that transforms an observation of all channels to the appropriate precoder for the common data stream. So, and a vectorized version of this appears here. So this is our goal of optimization. Yeah? We want to find an optimum value for AC. Yeah? And then we have also respective, for the equation 7, we have also respective vectors AP indexed by the number of the respective user. And this is the vectorized transformation A, P, and the transformation AP. These are the transformations that transform an observation, a contaminated observation. This is okay that this is contaminated. Yeah, it's designed for this contaminated observation. It takes the contaminated observation and generates the optimum precoder A at the end, because A, if you re-vectorize it into a matrix, you get the transformation with which you can find the precoder. So if you know A, the vector A, you know the precoders. So at the end, and here in the legend of this slide, you see that this is a very compact notation, and we have here tons of tensor products as a function of second-order statistics. You see here that the matrix C is the covariance matrix of all channels, of the block matrix of the channels, and we have here also the pilot information. So all data which is deterministic and which is known. Yeah, but we do not care about these details here. Just want to show this here. What we take care about is only here this typical pattern which we are used to have when we are talking about SINRs. So let's come to the problem formulation. And we do here the simplest you can do in such a system in a multi-user setup. We discuss the sum rate maximization problem. We can also talk about priorities of different users, or we can also go to the balancing problem. These are very similar problems. Let's do the simplest, and that is the sum rate maximization problem. For the rest of the talk, I will talk about this problem. And it appears as follows. You see this here. So we have a maximization of the common rate, RC, plus the sum of the private data rates. And you might have noticed that there is an LB here. That means that we are just optimizing, maximizing the lower bounds of the rates. And RC, the common data rate, is the weakest data rate that can be supported by the users, because once more again, we know that the common data rate must be decoded by each user. Yeah, so we have to choose the weakest data rate such that it really can be decoded by all users. And therefore, we have here this constraint that this expression of common rate that is contributing here to this overall rate, that this is the weakest potential. The weakest potential common rate. Yeah, this is a specialty here of this optimization problem, because of course, if we would take away, for example, the weakest user, we would have a larger, smallest common data rate. Yeah, so this is here implicitly taken into the constraint, and then we see two other constraints. We see here in the last line, we see here the average power. This is here the squared norm. So Euclidean norm stands for the power of the common precoder, and the common precoder, the average power of the common precoder is bounded by a fraction alpha C of the overall power budget. Yeah. So of course, then consequently, 1 minus this fraction alpha C times the overall budget of power is the power which is available for the sum of precoders to the private streams, for the private streams. And we see here that this is decoupled. We have here a sum of powers. This is just because we have independent data processes which are transmitted to the users. So this is obviously, and this is well known, this is obviously a highly non-convex optimization problem, and this is an issue. So how to solve this? It's intractable in practice. Yeah? So how to solve this problem? And there is a standard technique that has been proposed in this area. This is the iterative weighted MMSE algorithm. We will talk about this later, but let me first show what we're proposing. So we propose an alternating approach, and this alternating approach is consisting of 3 parts. It consists of a part where we just take care about the private optimization problem, so just optimizing the private rates. And to this end, we assume that the power fraction alpha C, which is balancing the power between private and common data streams, is fixed, and also the private precoder, the common precoder PC is also fixed. Yeah? This means that we just have to take care for the private data streams. Anyway, the common precoder has no impact anyway, because we assume that the interference of the common data stream is taken away by the successive interference cancellation at the receiver. So we get here problem 9. So problem 9 is just maximizing the sum of private data rates. The constraint here is the power limit, or the power budget, the constrained power budget. We will talk about the details of solving problem 9, because problem 9 is of course still non-convex. And then the problem 2 is, it's just the other way around, where we assume that we still have a fixed fraction of power dedicated to common and private operation, but we have now a fixed private precoder. We have fixed private precoders. And that means what remains is the optimization of the common precoder. And this is the maximization over the weakest SNR expression, Y common, the weakest SNR expression. Therefore, the minimum of the potential SNRs of the K users constrained to the respective power budget. And we will also talk about how we try to solve this. And then the third element of the solution in this alternating approach is that we have to find an optimum power fraction. And this power fraction alpha C, it's somehow between 0 and 1. And this is found by a kind of line search based on a particular method on the which you will see later. Yeah. Okay. Yeah, if you have any question during the talk, Lina is just posting this on the chat. If you have any question during the talk, please feel to raise your question here, of course. And you can also stop me anytime. Yeah. So let me continue now with these 3 parts. Yeah. First, we start with the private precoder. And this is the optimization problem again. We see here that we have this vector A. A is the stacked matrix, stacked vector of the vectorized vectors of all these transformation matrices. Yeah? If we would know the AP1 up to APK, yeah, if we know these matrices and we have instantaneous contaminated observations of the channel, we can find the optimum we can find a precoder. And we want to make A optimal such that the precoders are optimal. Yeah, but it's 1-to-1. The relationship of A and the precoder is 1-to-1. Yeah, so we see here the private precoder in equation 11. The solution of the private precoder is related to this optimization problem. We have this maximization over the sum of these log terms, and these SNR expressions depend on A. And then we have the constraint on the power. The problem, this is a non-convex problem still. And here in the bottom of the slide, you see again the expression that we have seen already before. This is the equivalent SNR expression. Yeah? It depends on A, on the AP respectively. Yeah? So what does this mean? how do we solve this? Because it's still non-convex. And we solve this now, and this is now the third element of what we combine, because I said we combine our bilinear precoder concept with rate splitting, and also using novel techniques from fractional programming. Yeah, and this is what we are doing. And this is work by Kaiming Shen and Wei Yu on a new kind of transformations to get rid of the fractions in this non-convex optimization problem. Yeah, and this is done what they call the Lagrangian dual transform and a quadratic transform. So what is the first step? The first step is that we find an equivalent optimization problem of 11. And then equivalence can be shown that equivalent to 11, we have this problem here. And this looks a bit weird. What's the reason for this problem? If you are not familiar with fractional programming, which I assume for the most of you here, therefore I tell a few words about this. What happens is that we try to get rid of, let me go back, we try to get rid of the gamma from the logarithm. Yeah? We try to get out the gamma out of the logarithm. And this is done by this. You see now gamma is externalized. Yeah, this SNR expression is now no longer in the log. In the log, we have now an auxiliary variable or a slack variable alpha k. And the nice thing is we have now this additional variable alpha k. So we have the a's. This is the variables that we had already before. And then we have now additional variables alpha. And why is this good? Because what we can show is if we fix a, yeah, if we fix a, the actual argument we want to go for, if we fix a, then we can show that this alpha that is minimizing this function, that is maximizing this function, sorry, is exactly the gamma which you would get if you would plug in a. Yeah, so it's this gamma here that you would have if you plug in a. Yeah, so in other words, this is just an intermediate variable, this alpha. Yeah, you could say if you know a, then this alpha optimal in this equivalent optimization function here is just a function of a. Yeah, and why is this good? Because we can now alternate again between a and alpha, and we can solve this problem here. Yeah? So it's just a trick, and this trick is typical for fractional programming. Yeah? So we are first externalizing here this logarithm, and that's all. Yeah. So with this observation, we can actually say that the original optimization problem looks now like this. You know, we come from 11 here now to 12, and you see we got rid of the log. We got rid of the log, but we have still the problem that the SNR, which is a fraction, and therefore it's non-convex, still is there and still appears here in the numerator and in the denominator. So this is not yet a convex optimization problem. It has still the issue of being non-convex. And here comes the second step, which has been proposed, the so-called quadratic transform. And I show you this on the next slide. And this is a little bit messy, yeah, to understand this ad hoc. So what we do is we again find a replacement for the objective function. The objective function now looks like this. And we have again introduced an auxiliary variable beta. We have still a, because a is the candidate we really want to optimize. And now we have a beta, and beta is an auxiliary variable. And we have replaced the optimization now by this guy. This is quite weird, yeah? And I don't want to explain this, why this works. I really recommend to check the paper and to read the paper by Kaiming Shen and Yu Wei. But what you see here is this auxiliary variable appears here in a quadratically, and this is the reason for the name here. Yeah, and it is also just a reformulation of the original problem in order to get a different shape. Because the nice thing is now that you are again alternating between a, what you actually want to have, and beta. And the nice thing is now, if we keep the one fixed, yeah, then the other one is now a convex problem. And that is the best you can achieve, that you have a convex problem. Let's see what happens. So what I said is we have now this formulation where we have A, this is the vector anyway that we wanted to optimize, and we have this auxiliary variable. And we found this after this previous step of getting rid of the log. Yeah? Don't forget this. And then we are here. And then let's look how we can solve this. And how do we solve this? We fix A, as I said, we do this alternatingly. We fix A, and when fixing A, we can directly in closed form solution say what beta is. And if we fix beta, we can almost directly in closed form say what A is. I almost, because the only thing that cannot be found in closed form is this lambda here. There is a scalar remaining, and this scalar has to be found by some bisection. Well, the nice thing, let me put it in a nutshell what we did. We had actually this problem here. We tried to get rid of the logarithm. This is a typical step in fractional programming. This is done by this idea. Then we come to equation 12, and the equation 12 is now we got rid of the logarithm, but we have now the problem that we have that we have expanded the number of variables because we need this auxiliary variables alpha. And then once more again, this can be again replaced by adding another auxiliary variable. This is more expanding our arguments. So the number of arguments is growing, yeah? But now we have a problem that can be solved alternatingly with problems which are very, very easy, even convex. Yeah, and that's a good point. But be aware, we have not made a non-convex problem to a convex one. Yeah? The problem is non-convex. We have a workaround here. Yeah? This is not necessarily the optimum solution. Yeah? Be careful. So, okay, now these are the steps. And let me come now to the common precoder. The common precoder is a very similar problem, and I won't spend so much. No, sorry. Yes, no, this is the second part. The common precoder is a very similar problem. I won't go in so many details, yeah, but it has a few subtle differences. What we first have to do is we have to maximize the minimum SNR, yeah, because we can only, once more again, this never forgets this in a rate splitting, the users, you can only support the common data stream that is decodable by this weakest user. Yeah? Therefore, we have to maximize the minimum SNR of all users. But we at least potentially consider all SNRs, yeah? All common SNRs, but at the end, we can only take the weakest. Yeah? Can only support the weakest. So this is equation 16, and you see here this expression that we have already seen in one of the previous slides. We have this expression here, and forget all these compact details of the compact notation. The only thing you have to put your attention to is the vector AC. AC is now the vectorized matrix AC that provides the precoder for the common data stream if we have an observation of the channels. Okay, this is a problem that has to be solved, and we do this again first by a standard step in all of these problems where we are maximizing over the pointwise minimum of a finite set. Yeah, this is by just introducing a slack variable set, and the slack variable set all SNRs must be larger than this minimum value. That is clearly, by this constraint, that is clearly the minimum of all SNRs, and this is replacing here this little awkward formulation in a more convenient formulation. Yeah? This is a typical step. And then we do the same as we just have seen before. We apply this quadratic transform proposed by the mentioned paper, and we come up with this here, and you can check out that this is quite same. Yeah? It's the same cost function. It's just in a different version introducing auxiliary variable. The auxiliary variable here is eta. Yeah? And then we do the same story. We have now a problem in eta and in A. Yeah? We have one more variable. You have AC, you have set, and eta. Set is the slack variable, and eta is this auxiliary variable that comes with this quadratic form. And why do we do this? Why do we do this? This is this typical trick in fractional programming. We try to replace the cost function such that we have a problem where we can, so the problem is identical, yeah, but then by this alternating optimization, we introduce some heuristic. So this is here, this AC, yeah, if we fix AC, we get the optimum auxiliary variable in closed form, but unfortunately not vice versa. So if we fix eta, we get a convex optimization problem here, and that must be solved by CFEX or by some other techniques, but it's at least convex. Yeah. We also will propose and tried some other techniques. For example, we used the multicast pre-coding algorithm that we proposed 15 years ago. There is a student of us, of Michael and mine, Raphael Hunger, and he at ICC 2007, we proposed a quite efficient method for multicasting. This can also be used here, and you will find this in our upcoming journal paper to this topic. I won't go into too much details here. We can solve here this common precoder problem. Okay, at the end, we have still the third problem, and this is the power fraction. So you see, this is a very involved problem. Yeah, we have to take care for the private streams, we have to take care for the common data streams, and now we have to find actually in advance or always, because this is alternating, we have always find to have a better, even improving power fraction. Yeah? How is this done? This is done by the golden section method. Yeah? So we have AC is of course between 0 and 1. And then by the golden section method, we find two candidates for AC, AC1, AC2. Then we compute step 1 and step 2 in order to get the sum rate. We based on these two power splits. Yeah? And then depending on which of the powers is the better one, we can cut off a part of this interval here. And then we do this again and again and again. And then the interval is cut off and cut off and cut off. And the interval shrinks and shrinks. And we stop until the size of this interval where we know that the optimum value for the power fraction lies in. If this fraction has a size which drops below some threshold. So this is the idea. This is very well known to be done with golden section method. Yeah, this is a method from the 50s. Okay, so what is state of the art? I just don't want just to present you our result here. I want to compare it, of course, with state-of-the-art solutions. There might be many solutions, heuristic solutions, and so on. But at least when you look to the literature, of course, here in the webinar, there have also been introduced many different ideas and techniques to different problems. But a standard vanilla algorithm of this sort of problems is clearly the iterative weighted minimum mean square error algorithm. The reason is because it's a quite beautiful algorithm. The theory is very attractive. Yeah, it's very nice to understand. It has to do with this relationship between SNR and MMSE, and there is nice properties from a theoretical point of view. Typically, there is an issue. Most scientists reported and engineers reported that there is sometimes an issue with convergence, but we leave these outside for a moment. Let's just see what happens. So in the iterative weighted MMSE, we do not deal with SNRs, but how the name already says, we are dealing with mean square errors. Mean square error of the private data stream, mean square errors of streams, and mean square error of the common data stream, of the potential common data stream. So at the end, we take not the smallest MMSE, we take the largest MMSE, because the largest MMSE of the common data streams is related to the weakest stream of weakest common data stream. So then we have here this relationship between the SNR and the MMSE. This is very well known. We have here again an expression of the SNRs. And attention, please. Here we talk about instantaneous SNRs, yeah? Because the iterative weighted MMSE is based on instantaneous channel state information. So here we have to take directly the observations of the channel. And we can, it's not a standard technique to somehow use second order statistics. Yeah? There are some proposals that do this, but it's not clear here for the moment how it is done here. Yeah? So we have not taken into account this. We just take, and this has been done in other works as well, we just take the SNR, but what we do is we take an MMSE estimate of the channels, and the MMSE, we do not just take the observations of the channel, we take an MMSE estimate, which has a decontaminating effect anyway. So we have here some details. I don't want to go into these details because it's an own method, which is a little bit complicated, but I guess this is quite well known to the audience, or to most of the audience. So we end up with an optimization problem where we are not maximizing now SINRs or rates, but where we are minimizing the sum of MMSEs. Yeah? And this can be done. This can be done because we have introduced extra weights and so on and so forth. As I said, I don't want to go into these details because they are quite known to the majority, I believe. So at the end, we can say that this problem 17 is very much related to the problem I introduced in the very beginning. Yeah? It's the same, just in a different notation now with MMSEs and with other kind of auxiliary variables. So we can again reformulate this using the quadratic transform that has been introduced before. We can somehow massage this problem, and then what we need, we solve it somehow. There are many techniques to solve this. Iteratively, what is important is where do we get the channel state information, and therefore we assume here that an MMSE estimator, a conditional mean estimator, an MMSE estimator, linear estimator is available. Yeah, and this is if we have, and therefore I was not completely right what I said before. We are using second order statistics, but just in the way that we try to find the optimum channel estimates. Yeah? And this kind of estimation is known to have some decontaminating properties. So we try to get the best out. This is an estimator. This is typically not affordable. Yeah, you know this. This is typically not affordable in massive MIMO because it's very huge. Yeah, but nevertheless, this is what we assume here. So we just provide the best what we can do on channel state information to the iterative weighted MMSE. What can we say already without looking at the results? What we can say about the bilinear method and the iterative weighted MMSE method is we can say that the bilinear method, our method, depends on the channel covariance matrices and instantaneous observations of the channel, but no channel estimation, just observations of the channel via a training sequence, and pilot contaminated, of course. And what we have to do is what is the numerical effort here? Unfortunately, I won't be able today to show you a detailed analysis of the numerical complexity with the respective methods. But what I can say here is that we have just this matrix vector multiplication with the matrix A. Yeah, in order to get a precoder, we get an observation of the channel, we multiply it with the matrix A, and the matrix A is quasi-deterministic, yeah, because it has only to be updated. These are the bilinear precoders. They only have to be updated when the covariance matrix information changes. Yeah. Instead, in the iterative weighted MMSE, what we need is an updating for each observation. Yeah, anytime when we get a new observation of the channel, we have to, because it's based on instantaneous channel state information, we have to completely compute the precoders again. Yeah. But on the other hand, we do not have to solve CVX problems and no fractional programming and so on. So it's not clear how the complexity relates to each other. And I won't talk about this today, because today I want to talk about this proof of concept. Yeah. So, but it's clearly a disadvantage, might be a disadvantage of the iterative weighted MMSE that we need updates not in the coherence interval time regime, but at any new estimate of the channel. Yeah? Yeah, this is what is said here. let me, you're certainly looking forward to the numerical results, and I have to a little bit watch the clock. The numerical results, what have been assumed here, we have an urban microcell environment, and we have used the 3GPP model here with 9 non-line of sight channels. So that means that we have a multi-path model. We have n paths consisting of n clusters, and each clusters consist of 20 propagation paths, rays, yeah, called here rays. We are assuming here 64 antennas, which is moderate for massive MIMO. We have 64 antennas. We assume that we have 5 uses, single antenna uses. They are distributed uniformly in a cell of 250 meters. The channel is, as typically in these 3GPP models, the channel is generated with this outer product of steering vectors at this, we have a uniform linear array. At this uniform linear array, we have the steering vectors, and with this outer product, this is the way how the covariance matrix is generated. And based on this covariance matrix, we are sampling the channel. So we have here a Gaussian channel model, but conditioned here on the directions, on the clusters, and so on. And what we also assume is we have 8 resource blocks for the downlink training that compared with 64 antennas. So you see we have here a severe pilot contamination, probably. Yeah. So we have not 64 accesses to the channel, but just 8. Yeah. So this is an example of the environment, how it happens. It could be, you know, it's the blue triangle in the middle of the base station, and then we have these 5 squares which are indicating the location of the users. And do not forget, this is non-line of sight. We have at least 6 clusters at each user and many micropaths. What are our numbers which we are analyzing? We consider the average sum rate based on the instantaneous channel state information, because of the numerical result. For the numerical results, we know, of course, not the algorithm, but we know, of course, the instantaneous channel state information. So we can apply the precoders, we can compute the achievable data rates, and we take the average here. We take the average here for the common data stream part and for the private one. And if we have no if we have no rate splitting, then the common part is, of course, not here. Yeah, though this is for the rate splitting, and this is with no rate splitting. And here we have these expressions that have been used here for the instantaneous common and private SI and Rs. Once more, again, remember that this part, which is taken into account, this SNR, which is taken into account for the common data rate, is the weakest of all, because a common data rate must be decoded by every user. So the results are averaged over 300 channel realizations, and this is what we see. So what we have here is the dashed curves is the lower bound. This is optimized. So the optimization is really on the lower bounds. Yeah. So you see, even for the lower bounds, we see the improvement by introducing rate splitting. The rate splitting has a gain if we have higher SNR. Yeah. If we have higher downlink power, yeah, the power budget increases. The rate splitting has here an improvement, and for the true values, this is even larger. Yeah, so this is the bound, but the bound is, of course, below the truth. Yeah, so we have here the red curve. This is without rate splitting, and the blue curve is rate splitting. This is the method that we propose, these 3 steps, yeah, where we are alternating between these fractional programs for the private data rate, the common data rate, and the power fraction. This is what we can achieve with this method. So if we have a closer look to the 5 uses here, then we see what is what can be often observed is that we see that for the low power, not all private users are switched on, yeah, but the common data is always on, yeah. And this is very interesting, for example, and unfortunately I'm not able to show you results, but this is very fortunate if we, for example, talk about minimum rate requirements, yeah. But this is here just sum rate, and for sum rate, of course, users can be switched off, yeah. But we have always a portion here of the common rate, and then we increase power. And interestingly enough, is that the share of the common rate of the overall rate even decreases, and then it increases again, and we have then, of course, this improvement that we saw in the slide before. This is for the proposed method. Let's now compare with the iterative weighted MMSE, and that's a very surprising result. Yeah, you might want to discuss this later on because you find it a bit drastic. Yeah, we also found it drastic. It's an interesting result. We see here that the iterative weighted MMSE has huge problems to cope with this contaminated data, because never forget we have here severely contaminated channel state information, yeah, and there are 2 ways to deal with this. The one is if there are no more resources, yeah, if you can spend more resources to get rid of contamination, if you have more resources to solve the inverse problem of the channel estimation perfectly for all antennas, okay, this is a different story. But here we assume we don't have, and then we have 2 options. We live with this problem and try to compensated by the techniques. This is our proposal. Or we try to use the standard vanilla technique, iterative weighted MMSE, but before we try to decontaminate the channel. And this is done here by a very advanced estimator, the best estimator you can have for a Gaussian process. It's the Mmsc Estimator. Yeah, and this is based here on perfect information about the covariances. So in some sense, you can say maybe you can do it somehow better to decontaminate, but we have actually full channel state, full information about the covariance matrix information, and we try to use this decontaminated channel state information and apply it to the iterative weighted MMSE, and you see that we have a drastic loss. Yeah? It remains a problem, this contamination, whereas our method works quite well with this. And we again see here now, so the blue lines are the proposed method, the purple lines are the iterative weighted MMSE, so to say the standard method, and the dashed lines are the without, and the solid lines are with the rate splitting. So you want to certainly see now what happens if the second order statistic is not perfect, because this is often assumed to be known, but what happens if we have to estimate it? And there have been some proposals also from my group how to do this. Yeah. So if you have estimated covariance matrix information now, you have a degradation, of course. Yeah, you have a degradation. You see here the degradation, the dashed curves are for estimated second order statistics, the solid curves are the cis curves from before. And this is here for using rate splitting. And you see again that there is no difference of the ranking between using the standard technique and the proposed technique. Yeah, that's it. My conclusion for the moment, because this is very ongoing work. Yeah, it's very recently that we found this and we had this result. And in my opinion, in our opinion, we found an efficient approach for solving this actually intractable sum rate maximization problem. It's a combination of what we call the bilinear precoder. You might call it generalized maximum ratio combiner. You might call it a statistical, a deterministic precoder, whatever. Yeah. Let's see what kind of terminology will succeed. And it's based on this new fractional programming techniques. And yeah, what has been shown is that the proposed result is very robust, in our opinion, against this contamination of the data. So it seems to be a good solution for FTD systems where you have always this issue that many parameters have to be estimated because of these massiveness of the system, and that you have really an issue with these ill-post inverse problems during channel estimation. And you might improve the inverse problems. Yeah? You might put all your effort into the inverse problem in order to estimate channels better. This is the one direction. Or you might try to live with it in a most robust way. And this is a proposal for doing it like this. So, okay. Thank you for your participation today and your attention. Thank you.
Thank you. Thank you, Professor Utschick, for a very interesting talk. And we have one question from the chat box. So the question is, what method was used to estimate covariance metrics in the next to the last slide?
Yeah. The method that was used here was proposed in signal processing letters a few years ago. There are also other groups that have made proposals. This was a work by my former student David Neumann and together with Michael Johann. The idea is that, because a typical question that you might have in mind who asks this question is that, how do I estimate the covariance matrix information while I have only contaminated signals? Yeah, because as I said, I have only contaminated signals. So how can I estimate the true covariance matrix? How can I get rid of this contamination for the covariance matrix estimation? And it can be shown this is doable by the following. So you try to design the estimation problem in the following way, that you run a pilot protocol such that you combine groups of different users, yeah, that gets the same training sequence for, yeah, or different or groups of antennas, yeah, and you do this, and by having multiple groups which do not share the same users, yeah, or not the same antennas, you can create an inverse problem that is invertible. Yeah, you can improve this, and this is a bit complicated, so I recommend really to look it up. This is Neumann, Johann Utschick at IEEE signal processing letters a few years ago, and you will find also a reference in the slides, because I guess you anyway will ask me to upload the slides, Lina, I guess, and then you will find a link to this paper.
Yeah, so if you are interested, maybe you can go to the paper for more details. So actually, I have several questions. Indeed, I'm very surprised by the comparison, the result from the proposed algorithm with the WMMSE. So I'm trying to understand that more. So do you mean that because you mentioned that the WMMSE requires instantaneous CSI, right? So but in the system model that you considered, you do not have this perfect CSI. So even when we do not have this CSI, you consider to choose an errored channel to do the WMSE. Am I correct?
I'm not sure if I understood you correctly, but I will share my slides again. Then maybe. So for the iterative weighted MMSE algorithm, we use Cis Channel Estimator. So we have YK. YK is, if I go in the very beginning, YK is an observation of the channel HK via the pilot matrix phi. Yeah? This is these observations are always used. We have to know something about the channel. Yeah, this is the observation of the channels. This observation is contaminated because phi, the matrix phi, is not invertible. Yeah, because we have not enough resources to resolve all degrees of freedoms of the channel. So this having this observation, what we do is, what we do the best we can do. Yeah, we take the estimator. Here we have this covariance matrix information. There's a lot of prior information. Yeah, the same information that we use in our method. Yeah, we have also we have not more information. We have this observation YK, and we have the covariance matrices, and we have access to the pilot data. So but we do not apply such an estimator. We do not apply the channel estimation. We do not make channel estimation. We just take an observation provided by the pilots, but then we do not plug it into some estimator that is used. This is a Bayesian estimator. Yeah? We do not do this. This is heavy, yeah, in complexity. We don't do this. We just take the observation, and what we apply is a matrix A, which also depends on second order statistics, but you do it only once. Yeah? So it's a fair comparison, I would say, because this guy here, this estimator, is only updated every time when the covariance matrix information changes. And it's the same for us. Yeah? But we do not put this effort into the estimator. We put the effort into these matrices A, yeah, these transformers. Okay? So this is what we compare. I don't know if this answers your question. Maybe
maybe I need to understand this more, because you know, the reason I raised this question is because in my previous collaboration with another student, she already came up with a WMMSE algorithm, which only considers statistical CSI. So maybe the method we consider is different. Like as you mentioned that you consider the channel estimate as a covariance matrix multiplied directly from the channel estimate, but we only consider the distribution of the channel for the WMMSE. Yeah.
Let me say following. Yeah. Though I said I'm comparing with what everybody is comparing with. I think this is fair enough. I compare the standard. For example, there is a work by Emil Björnsson. He does the same. He takes this as a comparison. Yeah. So I have channel estimation, which is not perfect.
Yeah.
The reason is this pilot contamination, but I can use the second order statistics to get out the best of this contaminated data. And then I have the channel estimates, and they are plugged to the MMSE estimator, MMSE precoding technique, because it needs instantaneous channel states. Otherwise, it doesn't work. This is the way. Yes, I'm aware that there are some proposals to apply the iterative weighted MMSE also for just second order statistics.
Yeah.
For example, I remember a work by the group of Tom Liu. Tom Liu has a work. What he does is he takes a covariance matrix and they estimate it, and he generates based on the covariance, but he generates realizations.
Yeah, samples.
And then he has a stochastic iterative weighted MMSE.
Yes.
I didn't check it here because this is not state of the art for this kind of methods, I would say. And in particular, he is on the other extreme side because he has no channel state information at all.
Yeah.
He has only covariance matrix information.
Exactly.
Here we have the situation that we have second order statistics, and we have at least a corrupted estimate of the channel. This is somehow between, and therefore, we will also look into this. By the way, yeah, we also look into this to use Tom's concept for this. Yeah, but this is not state of the art. Therefore, I did not report about it.
Yeah, I fully understand. So the major difference is that there is certain channel estimates considered in this work, which is different. So actually, this might be related to another question from mine. That is because you optimize this AK, right? So this AK is like a mapping from it to a precoder. So my question is, why don't we directly optimize precoder, but consider this AK, because the dimension of this AK might be larger than a vector of the precoder.
So once more again, I guess I share again here. No, this is I'm very grateful for my co-authors, are also grateful, I guess. We are very grateful for these questions. Really, that's a very good question. So let me go to where we introduce this. This is this kind of where we do this, yeah. And you said, why do we have this here? Yeah, why do we not directly take PC and the common precoder and the private precoders and directly operate with them? Why do we do it like this? The reason, this was by the way the motivation to call it a bilinear precoder, because if this would be an equalizer, this is where it came from. Actually, we developed this concept when we were studying equalizers, because we did the following. You have an observation of the channel, and based on this observation, you want to design the equalizer or the precoder, right? And then you have this precoder or equalizer, and you apply it to the received data vector. Mm-hmm. And this is the bilinear nature of what happens. Yeah, we have actually we have two vectors. We have the vector of observations of the pilots, and we have the vector of data that is receiving, that we receive. And then we see that actually it's a quadratic form. Yeah, it's a bilinear function based on a matrix A or any kind of matrix that provides the estimate of the data at the end. This is where this originally this idea bilinear precoder came from. But referring to your question, don't want to avoid your question. What you said is, why having this construction, why decomposing this into these two parts? The reason for this is that we can show that based on the hardening bound, we can relate the optimization only to AC, which is on a long time scale. Yeah, we can do it. We don't have to do it so frequently. Yeah? So Y is an instantaneous information, but A is a more or less quasi-deterministic information. So the nice idea is that with this stuff here, where is it? Sorry, here. With these bounds here, yeah, we are able to define, because these PCs here are replaced then by the A's, yeah, here. And the A's are just the vectorized transformations. So based on these hardening bounds, all the whole optimization is just based on the deterministic part of the precoder. So in other words, maybe it is better understandable. The proposal is that we compose the precoder into an instantaneous part and into a which is random, and into a deterministic part. The random part of the precoder depends on the random observation of the channel, whereas the deterministic part of the precoder depends on the second order statistics. And by doing this here like this, we can nicely use the framework of hardening bounds and the optimization stuff and so on.
I see. So it's just a joint utilization of both statistics and at the same time, instantaneous observation. Yeah, very interesting. Yeah, thank you very much. And one last question. Sorry, I have many questions.
I have 10.
Yeah, one last question is because the algorithm we proposed consider utilizing this fractional programming for optimizing the precoders of both common and the private parts, right? And we need to utilize a line search to find the optimal power allocation between the two parts. So my question is, why don't we directly utilize this fractional programming to jointly optimize both common and private part to get rid of this line search?
Good idea, but we couldn't manage to do this.
Okay.
It turns out that this is a bit tricky because of this coupling. You get too many couplings, and maybe we have overlooked something. Yeah, maybe it's doable. This is, of course, a good motivation to look for. But for the moment, we were not able to do this in one approach. Yeah? So it turned out that this is the better way of doing it. So, but yeah, this is definitely a goal. Yeah, maybe, but at the end, it's also a question of how much then the convergence would suffer from. You know, once you leave this convex stuff, yeah, and then you start with some heuristics, yeah. Then it becomes quite unclear. Yeah,
Yeah, I fully understand. Yeah, indeed, the existing proposed algorithm that you just mentioned can utilize the some good performance. For example, for multicasting, we can get some closed form something, and for the private part, and we can utilize some existing results. Maybe, yeah, this might be a good way to reduce the complexity. This is what I understand.
Yeah, because this is a good keyword, what you mentioning, complexity. I was not showing complexity considerations analysis here. This is a bit tricky because for the moment, we have not really a rigorous analysis. We have just an impression. Yeah. So to be honest, this fractional programming is costly, of course. Yeah, this is costly. But we ran it for the moment just on some notebooks. Yeah, so it takes a few minutes. Yeah, but you only have to do it for the whole scenario. But you only have to do it in this coherence interval. You don't have to do it all the time. So a fair comparison. We have some results, but I think they are not rigorous enough to show them. Yeah, because maybe we would be unfair. I don't know. Of course, this will also be a question how to get rid of complexity. Yeah, we have done something in this. I think that the most expensive, it might also be your experience. The most expensive part is common precoder.
Yeah,
and there we had done many experiments. You can do heuristics. You can, as I said, we have been using old techniques for multicast beamforming and stuff like this. So there are different workarounds possible. Yeah, it is not yet clear. Yeah,
there are actually some low complexity precoding, some kind of like a closed form, but the performance obviously will not be as good as for when the precode is optimized.
If you would ask if what is the maybe it's too early to make an overall conclusion, yeah, because these are preliminary results. We will publish them this week. They will be on archive. Then you can in the slides we will put an archive link. Then you can see the latest results. So, but so it's too early to make conclusions. But I think because you said you have experience with the Mmsc. I was also talking with Eduard Josvik. He was also doing a lot with this. We agree that it's a very smart technique, the iterative weighted MSE, but it has really issues with convergence, and it is very, very sensitive to initial conditions. Yeah. So this is something that I saw we had some publications before at ICC. Yeah, I think this was this workshop that you guys were organizing as well at ICC or the PIMRC. I think we had some papers on this. Yeah. And there we are using the iterative weighted MMSE, and it's extremely sensitive to initial conditions. You can do it smart, you can do it not so smart. You have to have a good intuition. And actually my impression is, yeah, so this is academic work, what we are doing here. But once you want to bring this ever into an industrial product, yeah, I wonder if engineers want to run an algorithm which is so sensitive to the tuning parameters.
Yeah,
and this is something what we observed here with this technique, that this is absolutely insensitive. Yeah, you can initialize as you want and you come up with the same method. Yeah, but this is not the case for the iterative weighted MSE. There you have really to have a couple of starting initial conditions to pick out the best one. And this is my experience. Maybe we are just too dumb to do it correctly, but I don't know. So I talked with Eduard. He's unfortunately not here today, I guess, because he could also report on this, because we had a discussion and he told me he made the same experience. Very nice technique, but very sensitive to tuning parameters.
Yeah, indeed. But you know, we are always looking for those, you know, interesting and novel new algorithms which can help us reduce the complexity and at the same time maybe keep the performance. You know, yeah. Okay, thank you, Professor Utschick, for a very interesting talk. Any other question? Okay, so if no, I would like to going to end this webinar, but before that, I would like to introduce the upcoming events of our special interest group. So there will be 2 workshops in conjunction with ICC and WCNC 2022. Submission deadlines are January 20 and January 21 will coming soon. And then there will be a JSAC special issue on rate splitting, and the deadline is July the 1st. So it's longer from now to prepare a paper. And we look forward to your submission to these workshops and a special issue. Okay, and thank you so much, Professor Utschick, for the talk and for preparing this very interesting talk. Let me stop sharing first. And
yeah, I want to thank you also, Lina, and also Bruno, who was not here today. Send him my best greetings. Thank you very much for organizing this wonderful webinar. I also want to thank my student Donia, who put a lot of effort into the slides, and also my colleague Michael Johan, who supervised this topic together with me. So thank you to you and to my group, which is also here today. A majority of my group members is here as well. So thank you very much. And once more again, thanks to the organizers. It was a great experience to be here and part of this. Thank you.
Thank you all. And we look forward to, you know, to further collaboration or, you know, to further discussion on this topic. Okay. So Happy New Year, everyone. And I will end now.
Bye-bye.
Bye-bye, Professor Utschick.